video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA. Inferential statistics. Part 3, Estimation of population mean for small sample size and unknown population standard deviation.
Hello again. This session is continuation of what we've been discussing, which is inferential statistics. But this time we will move on to a different condition, which is taking small samples from a large population. In a previous session we discussed taking a large sample, and when we say a large sample, that's a sample of 30 or more. And we were hoping that the variance of the population is known. This time we're going to talk about small sample, less than 30, and that the variance of the population is unknown. So we really have double issues here. Sample size is small and the population variance is unknown. Let's go to the slides and see how we deal with that.
In the previous session, we discussed how to estimate population mean by taking a sample from a large population with a known standard deviation. So the key was a knowledge of the standard deviation of the population. And in that case, we used the normal distribution and the standard normal distribution to make our estimation analysis. Now we are moving to another situation. It's a more difficult situation where you have a population that we don't know anything about its variability, or the standard deviation, or the variance of the population. And in this case, we are trying to take a small sample from that population. And we defined a sample as being small or large by virtue of the sample size. We mentioned that a sample is small when it has a size of less than 30. And the sample is large when it has a size of 30 or more. So once again, we are going to deal with these two situations: small sample and a large sample. Now the common issue here is that the population standard deviation sigma is unknown. And once again, if we are going to deal with a small sample, we would hope that we can make the assumption that the population is normal. And if we are dealing with a sample that's large, then we don't have to make that assumption. But in both cases, if the standard deviation of the population is unknown, then we really have to use a different type of sampling distribution. And that's what we call the T distribution. So let us go and see how we go about using the T distribution in estimating population mean from a small sample without knowledge of the population standard deviation. Let's take this situation first. Sample size is less than 30. But we are willing to assume that the population is normal and we don't know the standard deviation of the population. And in this case, as I said, we need to use a t-distribution. So let us define first what is a t-distribution and what are the basic characteristics of the t-distribution. A t-distribution is a result of collecting small samples of a size less than 30, determining the means of these samples, and then constructing a frequency distribution or a sampling distribution of these means. So if the variable of the parent population can be approximated by a normal distribution, the sampling distribution of sample means of small samples will be called the t-distribution or the studentized distribution. The t-distribution is essentially a normal distribution, as we can see here. Indeed, it's a form of a standard normal distribution with a center or an average 0. However, the shape of this distribution will vary with what we call the degree of freedom. And the degree of freedom is essentially the sample size minus 1. Now, the t-statistic is calculated from this simple expression. It is x bar, or the sample mean, minus mu, which is the population mean, divided by the standard deviation of the sample, s, divided by the square root of the sample size. Recall that we call this term here s over the square root of n, the standard error. Again, the shape of the curve will be determined by the sample size or the degree of freedom lambda, or the sample size n minus 1, as we can see here. Some of the important characteristics of the t-distribution is that the t-distribution corresponding to any particular number of degrees of freedom is bell-shaped, just like the normal distribution, centered at 0, just like the standard normal z-distribution, and each t-distribution is more spread out than the standard normal distribution, slightly change in the shape. We should also know that the standard deviation of the t-distribution is determined by the square root of the degree of freedom divided by the degree of freedom minus 2. Recall that the standard deviation of the standard normal distribution was 1. Here it is determined by the size of the sample. What we see here is the standard deviation of the normal distribution. When we have a sample size of 10, that means the degree of freedom is 9. And in this case, the standard deviation of this t-distribution will be determined by the square root of 9 divided by 9 minus 2, which will give us 1.134. This is just an example. As compared to the standard normal distribution, which is this one here, which has a standard deviation of 1. So you can see that the typical t-distribution has a standard deviation slightly higher than the standard normal distribution, and as a result it is going to be slightly wider than the standard normal distribution that we are familiar with. And what does that mean in practice? It simply means that when we make an estimation, we're going to have a wider confidence as a result of the small sample size and as a result of the lack of knowledge of the standard deviation of the population, as we will see later on by examples. just as we did in the previous session, in formulating the confidence interval, and we had to find the value of Z at the confidence level that we established, 95% or 99% or 90%, we will basically do the same thing with the t distribution. You can see here that we have a more or less normal distribution, which is the t distribution in this case. The area in the middle here is the area of confidence or the confidence level. It can be 95 or 99%. And the outside areas to the right and the left represent the risk that we will take in our estimation. And here are the values of t, or the critical values of t. Now, if you recall, the critical value of z were determined simply by the area. So if we know the area, well, we were able to determine the z value. But in case of the t distribution, in order to find the t value, we have to know the degree of freedom determined by the sample size minus 1, as well as the area of confidence. As a result, we have to refer to the so-called the t table. And the t table will be looking something like this one here. You want to look at the sketch here, because this sketch really summarizes what this table does. You can see here we have an area to the right. Okay, this is a one-tailed area, which we will call it alpha. And we can see that the center here is at 0. And in most of our calculations, we will be needing the value of t at the area of confidence. And the way this table is designed, we will see that the first column here represents the degree of freedom. So any one of these values will represent the sample size minus 1. As a result, this column starts with value 1. Why 1? Because the smallest sample size will be of a size 2. And as a result, the degree of freedom of that will be 2 minus 1, or 1. And as you can see here, down the column, the sample size or the degree of freedom increases. Now, what we see in the first row here is the area in the right tail here. So this area here. So this can be 0.001 or 0.0025 or 0.005, and this will all depend on the confidence level, as we will see by example in a few minutes. Now the second row here represents double the area to the right tail. So if this is 0.001, this will be 0.002. If this is 0.0025, this will be 0.005, and so on. Meaning, if we do in a double-sided risk in this case. This table here has all the values, and as we will find out later on, the t distribution is very effective up to a degree of freedom of about 30. Remember, 30 was the threshold of sample size. A sample of 30 or more was considered a large sample. A sample of less than 30 was considered a small sample. And again, the effectiveness of the t distribution becomes much less above the value of 30. But we have the rest of the table here in case you are interested in values of t for degrees of freedom above 30. All the way up to infinity in case. Let us take some examples of how we find the value or the t value from the t table. The first example, find the value of t for the 16 degrees of freedom and 0.5 or 0.05 area in the right tail of the t distribution. So basically that is what we need. We have here the degree of freedom being 16 and it is this area that we are interested in, 0.05, which means that this entire area to the left here is 0.95 or 95%. And this is the t value that we need. In this case, we will go to the t table. And as you can see, I'm only including here the one tail row, which is this tail here. And at 16 degree of freedom, we'll go down this column here at 16. And at area of 0.05, we will look for the area on the top in the first row. So now we have the degree of freedom and we have the area, and the intersection between these two values, if we take a horizontal line here and a vertical line there, will give us the value of t that we are looking for, the 1.746. I'd like to point out that because of the symmetry of the t distribution, really when we find the value of t at the right tail, that is automatically giving us the value of t at the left tail, as you can see here. So if this is the value on the right tail of 0.05, the corresponding value on the negative side will be the value of the t at the left tail of the t distribution. Another example, find the value of t for the following cases: sample size 20 and the area is 0.005. This area here is 0.5%, meaning we have 99.5% on the other side. So here is the 0.005, which is here, and this area here will be the 0.995. Now in the t table, we have to look at sample size 20, meaning a degree of freedom of 20 minus 1 or 19. Here it is, and the area of 0.005 is here. So again, a horizontal line here and the vertical line there will give us the intersection or the value in the middle, which is 2.861, being the t value that we are looking for. Again, sample size 17, area of 0.05. If sample size 17, the degree of freedom is 17 minus 1 or 16. The area is 0.05. So we'll go at 16 and 0.05, and the t value will be 1.746. The body of the table give us the t value or the critical t value, as you can see here. Another example, sample size 21, area is 0.025, and we repeat in the analysis. Here it is at sample size 21, the degree of freedom is 21 minus 1, and the area is 0.025, and the value of t will be 2.086. And notice, if this is 0.25, then this entire area here will be 1 minus 0.025 or 97.5% of the area. This is how we obtain the values of t. Now let us go to the estimation aspect, where we're going to look at populations of unknown standard deviation, and we will be taking small samples. If the variable of the parent population can be approximated by a normal distribution, the sampling distribution of sample means of small samples, as we mentioned before, would be called the t distribution, and the variable of this distribution, which is the t statistic, will be determined by this equation here: x bar minus mu divided by the standard error, or s, over the square root of n. Now really, if we arrange this equation, we can obtain the confidence interval. And here is how it looks like. Again, as we mentioned in previous session, mu will be determined by a point of estimate, which is the x bar, plus or minus the margin of error e. The only difference now is that we don't know the standard deviation of the population and the sample is small and we are willing to assume normality. Then we have a new margin of error here determined by the t-value at the degree of freedom specified and the area and times the standard error, or S over the square root of n. Now we don't have the standard deviation of the population, so obviously we will have to rely on the standard deviation of the sample. This is clear here when we have mu equal the point estimate x bar plus or minus the t-value times S over the square root of n, or S x bar, or the standard error. Now, as in previous session, we typically are given all the values and the effort will narrow down to finding the value of t. Let's take an example. According to Kaiser Family Foundation, US workers who had employer-provided health insurance coverage paid an average premium of $4,129 for family health insurance coverage during 2011. A random sample of 25 workers from New York City who have employer-provided health insurance coverage paid an average premium of $6,600 for family health insurance coverage with a standard deviation of $800. And the question is about estimating the population average of the health insurance coverage. The question says make a 95% confidence interval for the current average premium paid for family health insurance coverage by all workers in New York City who have employer-provided health insurance coverage. Assume that the distribution of premiums paid for family health insurance coverage by all workers in New York City who have employer-provided health insurance coverage is normally distributed. What we need to pay attention to here is, number one, there is a value here of the average premium. But this is an old value. This is in 2011. So this value really is only a reference for us after we do the estimation, so that we can compare the current average premium with the premium on 2011. So this value is not going to be used in our analysis, except for the comparison purpose. But what we will use is, number one, we have 25 workers, so that is the sample size. It's a random sample of 25. That sample had an average of $6,600 for family health insurance coverage, and the standard deviation of the sample was 800. We also need to note that we need a 95% confidence, and even more importantly, that we are willing to assume that the distribution of coverage is a normal distribution. So these are the given. Sample size 25, average 6,600, and the standard deviation of the sample is 800. All of these are information from the sample. We really know nothing about the population variability here, and that is different from what we did before. Now, in order to establish a confidence level at 95%, and given what we are given, we really have to use the t-distribution in order to make our estimation. So first we calculate the standard error, which is the standard deviation divided by the square root of the sample size, 800 divided by the square root of 25, which will give us $160. And then we know that we need to establish a confidence interval or estimation at a 95% confidence. And when we have a 95% confidence, we have a 5% risk that we divide into two sides, 2.5% here and 2.5% here. So when we go to the t-table, we will have to look at a sample size 25, or degree of freedom 25 minus 1, which is 24, and an area of 0.025. That is the 2.5% in the right tail. And at these two values, we have a t-value of 2.064. We can take this value and substitute it in the inequality, and that will give us, here is mu, estimated by the point estimate x bar plus or minus t times the standard error. The point estimate x bar is 6,600, that's given, and the standard error we calculated a minute ago, and it was 160, and here is the t-value that we just found from the table, and that gives us the complete estimate to be 6,600 plus or minus 330.24. Or we have a range of estimation from about 6,269 to 6,930. Thus, we can state that with 95% confidence, the current mean premium paid for family health insurance coverage by all workers in New York City who have employer-provided health insurance coverage is between 6,269 to 6,930. That is now, that is currently. Recall from the head of the problem that our the average in 2011 was 4,129. So 4,129 in 2011. Now we are talking about a range from 6,269 to 6,930. Here is another example. 64 randomly selected adults who buy books for general reading were asked how much they usually spend on books per year. The sample produced a mean of $1,450 and the standard deviation of $300 for such annual expenses. And the question is, determine a 99% confidence interval for the corresponding population mean. Here we have a large sample, 64 randomly selected adults. And that sample produced an average of 1450 and the standard deviation of 300. We can go ahead and do the estimation here, despite the fact that we don't know the variability of the population, and we also are not willing to assume that the variable is normally distributed, only because the sample is large. And in this case, here is our sample size, here is our average, here is the standard deviation of the sample, which means we can calculate the standard error Sx bar, which is S divided by the square root of n, 300 divided by the square root of 64, and that gives us a standard error of $37.5. And we have a 99% confidence interval, then we are ready to estimate our population mean. And here is the equation. Obviously, we have to go to the t-table first and find the t-value, which came out to be 2.656, and this will be at 0.5%, because at 99% confidence interval we have 0.5% to the right and 0.5% to the left. Here you see 0.5% to the right and 0.5% to the left. So in the t-table we have to look at alpha being 0.5 or alpha over 2 in this case, and of course a degree of freedom of 64 minus 1 or 63. And the estimation yields a range from 1350.4 to 1549.6. Thus we can state that with 99% confidence that based on this sample, the mean annual expenditures on books by all adults who buy books for general reading is between 1350.4 to 1549.6. This example here deserves some attention because we have a very large sample size with respect to the threshold of 30, which is 64 randomly selected adults. And quite often, people, when they have this large sample, they ignore the condition of the standard deviation of population being known or unknown, and they go ahead and perform the estimation using the standard normal curve or the normal distribution. So let's assume that we follow what those guys are saying here. So we're going to repeat this example again, but this time we're going to use the normal distribution approach. And as you recall, at 99%, which is the confidence level we're establishing here, the z-value was 2.58. So if I substitute for this value in our estimation, which is in this case mu equal to x bar plus or minus z times s over the square root of n, it should be really sigma over the square root of n, but we are using s, or the standard deviation of the sample, as a rough estimate of the standard deviation of the population. Then in this case we will have 1450 plus or minus 2.58 times s divided by the square root of 64, which will be 8, and this will be the new estimate here. So this is 1450 plus or minus 96.75. Now let us compare this estimation with the previous estimation from the t distribution. When we used the t approach, the t value was 2.656 and the estimation was from 1350.4 to 1549.6. While when we use the normal distribution, the z statistic was 2.58. Notice it is less than the t statistic, and the estimation was that mu from 1353.3 to 15.46.8. And as you can see here, using the t distribution, our estimation is wider, meaning we have a wider range of mu estimated using the t distribution than when we use the normal distribution. This is a direct result of the characteristic of the t distribution that we mentioned earlier, that the t distribution is wider than the normal or the standard normal distribution. So what does that mean? It means if we have the t distribution, which is the wide one here, and the z distribution, the estimation for the t distribution was 1350.4 to 1549.6. While the estimation using the normal distribution or the standard normal distribution came out to be 1353 to 1546. And as you can see here, there is a difference between the two estimations. This difference may not be so large. See, this is 1350, this is 1353, this is 1549, this is 1546. So about 3 points difference in both cases. However, the t distribution gives us a wider range, and typically speaking, a wider range means a more safer estimation, because there is a chance that the distribution or the estimation may come out of this range, but the chance is lesser when we use a wider range of estimation. For this reason, a lot of people prefer using the t distribution automatically for a small or a large sample. Now you have to understand that if the normality assumption is not there or is not applied or does not hold, then the smaller the sample size or the smaller the degree of freedom, the larger the difference between estimation using the t distribution and the estimation using the z distribution. Now you can ignore all of this and adhere to the criteria that the t-distribution is typically used when sigma, or the standard deviation of the population, is unknown, and the z-distribution is typically used when the standard deviation of the population is known. This is the safest way in estimation. I simply thought that I will let you know, just in case that you see in some books that people are using the z-distribution when the samples are large, regardless whether sigma is known or not, and regardless whether the assumption of normality applies or not. Here is another example where we will have the opportunity to kind of review what we did in previous session in calculating the average and the standard deviation of a sample. A company making metal bars wishes to estimate the mean weight of the metal bar population. The company used only 10 bars, and they found the values of weight of these bars to be as shown on the table here. Here you can see individual values of bar weights of 10 bars. And the question is about finding a 99% confidence for the mean bar weight of the population, assuming that we know that the variable bar weight follows approximately a normal distribution. This is a problem for the t-distribution approach, straightforward. What we have to do here is we calculate the mean value of the bar weights by adding up these values divided by 10, and also calculate the standard deviation. And don't forget that when we calculate the standard deviation for a small sample of less than 30, we use the n minus 1 in the equation, not the n. So now we have the mean of the sample, we have the standard deviation of the sample, and what's left for us, of course, we know the sample size being 10. So what's left for us is finding the t-value at a confidence level of 99%, and we've done that before. So if we go to the t-table here, as you can see, at degree of freedom 9, because the sample size was 10, and at an area of 0.005, we have a t-value of 3.25, and we can substitute for this value in the inequality. And what we have here is a range of the bar weights from 2.061 to 2.359. So again, this is a quick review given the individual values of the sample or the sample observations. In order to estimate, we have to calculate the mean and the standard deviation of the sample as we saw it. Before I leave the subject of estimating the population mean mu, I have to address one important issue. We covered it before, but we have to recover it again to see its impact now that we know how to estimate the population mean. That is the subject of the effect of sample size on the estimated value of mu. Does the sample size affect our estimation? Meaning, if we take a small sample versus a larger sample, would a larger sample give us a better estimation? That is what we will see by example. What we have here is a real estate broker who was interested in the property tax paid for houses in his sales area. He took a random sample of 40 houses, so that's a larger sample, and they found that the mean of the annual property tax of these houses is 4,000, and the standard deviation is 1,000. Estimate the population mean of annual property tax at 95% confidence level. What is the sampling error or the margin of error? And what is the minimum sample size required to reduce this margin of error down to half its current value? In this case, if we follow the normal distribution approach, we will find that our estimation is 4,000 plus or minus 309.9. We are given X bar being 4,000. We given the sigma or the standard deviation of the sample, which we will approximate it as being the standard deviation of the population since the sample is large, of 1,000 divided by the square root of 40, and here is our estimation. The margin of error, the absolute value of the margin of error here is 309.9. Now, quite often we hear the margin of error as a percentage. We hear people saying 5% margin of error or 3% margin of error. The way this is calculated is very simple. We have the absolute value of 309.9 divided by the point estimate of 4,000 times 100. And in this case, as you can see, we have about 7.8 or 7.75% margin of error. So yes, we can express the margin of error as absolute value like the 309.9 or as a percentage of the average or the point estimate. Now, what if we want to reduce this margin of error to half of that? Meaning, instead of 7.75, we wanted half, or instead of 309.9, we wanted half of that. Well, in this case, we have established the tolerance, the E value in the sample size equation that we discussed earlier. At a margin of error half of this value, or 309.9 divided by 2, that's 154.95. Here is our equation of sample size. Remember, it is Z times sigma divided by E all square. Now we have the new E, which is the 154.95 or the 155 approximately, which is really the difference between the mean of the population and the mean of the sample. That is what we define the margin of error as. And we have sigma, and we have Z at 95% being 1.96. And look at what we have now. We have a sample size of 160. Now, remember the original sample size was 40. So jumping from 40 to 160, that is a large jump, a big jump. But the impact of this is that we're going to have half of the margin of error. Indeed, if we use this new n now in our estimation, we will find that as we go in the equation now, and instead of using n as 40, we're going to use n as 160, we will have mu being equal 4,000 plus or minus 154.95. Remember, the old one, it was 309. So now we have a smaller margin of error, which is now 3.9%. So the equation of sample size can be used to estimate the minimum sample size at some required margin of error. And that's a key aspect that I thought that I will close this session with, so you will know some of the merits of calculating the minimum sample size for the purpose of estimation.